All right, we are starting chapter 10 on parametric. Now we did a lot with polar coordinates in pre-algebra, so a lot of that part of it should come back. Since we've done parametric equations, we only did that briefly in algebra 2. Okay, so we're going to start just looking at how to graph parametric, define for parametric equations what they are. Okay, so the reason that we want parametric equations is because often we can't write a function for certain kinds of curves. So math is moving along this curve it's shown, and it's just moving in a path like this, and we want to just be able to have an equation to describe the movement of the particle. We can't write a function for it, which is clear because it doesn't pass the vertical line test, right? Fails the vertical line test. We can't write an equation. And if we don't have a function, it's hard for us to do calculus on it, you know, like taking derivatives and integrals and all those kinds of things if we don't actually have a function. And so parametric equations are sort of a solution to that kind of a problem. So certainly we can't write a function for this particular curve, but if we look at just the x-coordinate of it, like let's say this point right here, if we just look at the x-coordinate, that is a function of time. Okay, and the y-coordinate as well is a function of time. So if I can write a function with respect to time that gives me the x-coordinate and a function with respect to y that gives me the y-coordinate, then I can specify the location of that particle and hence, you know, all the positions on that curve with two functions. And that is what parametric equations are. Okay, so parametric equations. So suppose that x and y are both given as functions of a third variable, t, and we call that t the parameter, hence the word parametric equations. That's just because we have a parameter that both of the equations rely on. So I can describe x as a function of t, and I can describe y as a function of t. And then t is called the parameter. Okay, so those two functions there are called parametric equations. And if I were just to take the set of all the points, x and y, that are generated by these functions for various values of t, okay, so the way that I would find an x-coordinate is I would pick a t value and put it into this function and into that function, and the x and y that came from the same exact t value give me a point. Okay, so that x is what I get for f of t, and the y coordinate is what I get for g of t. So if I put all of those points together, I get something called a parametric curve. Now typically we think of t as time. It doesn't have to represent time. It can be any kind of third variable, but in lots of applications it does. We'll see that we'll use that third parameter as an angle a lot when we're looking at trigonometric functions as well. So the two common variables that we choose as the parameter would be like the time as the third parameter or an angle as the third parameter. So let's look at some examples. Okay, so let's say we have x is defined as t squared minus 2t, and y is defined as t plus 1. And we want to figure out what the graph of this particular parametric curve is going to look like. So we can start by just plotting a bunch of different points and see if we can figure out what the curve looks like. So I'm just going to pick various values of t. I put them in a table for us, and then for each t we'll get an x coordinate that's generated by that t value, and we'll get a y coordinate that's generated for that t value, and we'll just plot that. Okay, so when I put -2 in, I'll get 4, then plus 4, so this will be 8. and then for y, I'll have negative 2 plus 1, which is negative 1. So 8, negative 1 is going to be a point on my curve. I'm just going to label this. This is when t equals negative 2. And if I put negative 1 in, I'll have 1 plus 2, which is 3. And then for y, I'll have negative 1 plus 1 is 0. So 3, 0 is the next point. Okay, so if I were to just kind of, okay, if this were like a particle, at time t equals negative 2, it was here, and now it has moved over here at time t equals negative 1, if t represents time. Okay, at 0, we put 0 in, that just gives us 0, and then 0 plus 1 is 1. So this is where we are at t equals 0. If we put 1 in there, we'll get 1 minus 2, which is negative 1, and 1 plus 1 is 2, so negative 1, 2. This is at t equals 1. T equals 2, we'll get 2 squared minus 4, which is 0. And then 2 plus 1 is 3, so 0, 3. So that's at t2, so we'll come around this direction. And then at 3, we'll have 9 minus 6, which is 3, and 3 plus 1 is 4, so the point 3, 4. I'm coming this way, that's at t equals 3. And then at t equals 4, we'll have 16 minus 8, which is 8, and then 4 plus 1 is 5. Okay, and so 8, 5, and it comes around this way. Okay, and you can imagine if we continued with t equals 5, it would just go off in this direction. If we went back to t equals negative 3, it would come from back there. And it has this kind of a... Okay, so you can see if this represents the movement of something, it seems to be moving, okay, in this sort of sideways parabolic shape. So it looks like a parabola. Okay, you know, it's sideways, but still looks like a parabola. Okay, now if we take these and eliminate the parameter, we can find a Cartesian equation that just involves x and y that describes the curve as well. So let's go ahead and do that. So let's eliminate t by, just do it by substitution. It'll probably be a little bit easier because of the square in there. So let's solve the second equation for t. So if I subtract 1 from both sides, I'll get that t equals y minus 1. And then I can substitute that into the second equation. So I have x equals t squared. Whoops, I put y equals 1 instead of y minus 1. So t is y minus 1, so I'll square that. And then minus 2 times t. T is y minus 1, so substitute that in. So if I square that out, I'll get y squared minus 2y plus 1. And if I distribute the negative 2, I have negative 2y plus 2. And if I simplify that, I get y squared minus 4y plus 3. Okay, so this would be the Cartesian equation, and you can see indeed, you know, this is a quadratic. Okay, so it's a parabola. Okay, now normally think of parabolas as y being some function of x, where x is squared, but if I have x and then y squared, I just get this sideways parabola. Their axes just kind of get reversed. Okay, so this is indeed a sideways parabola function. Okay, so and that's also shows us a good way if we want to be able to describe it in a Cartesian equation, how we can eliminate the parameter. You know, you can use substitution or elimination, whatever, just depends on what's easiest. Okay. So, in the example that we just did, we kind of just, said that there were no restrictions on t, kind of said, well, if it came from here, it would, this could keep going on forever. And we're assuming that this kind of came back from forever as well. Now, in applications, often we're going to look and restrict that parameter to some kind of finite interval. For example, if it really were time, usually negative time doesn't make any sense. Maybe we're trying to look at a particle and what its behavior is between time 0 and 4, or time 0 and 10, whatever. Okay. So if, for the previous example, we restrict the time from 0 to 4, we just get part of that curve. Okay. And you'll see the little arrow on there that shows, this is an earlier time, and then it moves this direction, and this is a later time. So we identify, if we're talking about a closed or a finite interval, okay, the very first values, if I pick the lowest value of t and plug that in, whatever point I get, that's called the initial point. So in this case, this is the initial point because this is where it starts. Okay, and then as t increases from 0 to 4, it'll move along this curve here, and then when we get t equals 4, that will be the last point. That will be the end of that finite interval. And so that 0.85, where it stops, that will be the terminal point. Okay, so in general, and you see the arrow there is showing that it goes from initial to moving towards the terminal point. So in general, if we have parametric equations, x is a function of t, y is a function of t, and then t is in some kind of finite interval between a and b. Okay, the way that we find the initial point is we plug a, the lowest value of t, into the two functions to get our x and y coordinates. That will be the initial point. And then to get the terminal point, we take the maximum, the b value, and plug that into each function to get the coordinates of the terminal point. Okay, so we are going to look at the curve that's represented by the parametric equations y equals cosine t and y equals sine t, and we will let t vary from the smallest value of 0 to the largest value of 2 pi, which would be like 1 period of the cosine, 1 period of the sine, and we would sort of expect it to repeat after that. Okay, so I didn't put all values of t in here. I just tried to pick a few representative ones to give us an idea of what the curve would look like. So let's start at 0. Okay, so if I go to x, the cosine of 0 is 1, and the sine of 0 is 0. So because we're going to get small values, I'm going to make this go like by 0.2, 0.4, 0.6, 0.8, and then 1 is here. Okay. All right, and then at pi, let me plot that on there. So that's 1, 0. That's right here. This is our initial point, and that's at t equals 0. Okay, and then if we move on to pi over 6, the cosine of pi over 6 is square root of 3 over 2. Okay, and if we want to be able to plot that, which is a little bit tricky, it's nice to have a decimal approximation of that. Okay, and so our decimal approximation of that value is about 0.866. Okay, and then the sine of pi over 6 is a half, that's 0.5. So if I go 0.866, that's about here, 0.5, that's 2/4, that's about right here. Let me mark these as well. Okay. And then we go on to pi over 4. The cosine of pi over 4 is square root of 2 over 2, but that's approximately 0.707. The sine of pi over 4 is also square root of 2 over 2, or about 0.707. Okay, so that's about 0.7, and that's about 0.7. So let's see, this was at pi over 6. This is at pi over 4. So we're getting this kind of a movement at pi over 3. The cosine is a half, which is 0.5, and the sine is now 0.866. Those have swapped. So at 0.5, we're up at 0.866, so right about here. So it's moving this direction. This is at pi over 3, and then when we get to pi over 2, the cosine of pi over 2 is 0, and the sine of pi over 2 is 1. So here we are at pi over 2. You can see the angle is at pi over 2. And you might have kind of an idea of what you think this is going to be. Okay, if we move on to pi, which is, you know, think about our angle is opening up this direction still. Okay, what's going to happen? So the cosine of pi is -1, and the sine of pi is 0. So as our angle continues to increase, we're going to get to the point. This is -0.2, -0.4, -0.6, -0.8, and -1. So it's going to come down this direction. Okay, at 3 pi over 2, which is this axis right here, the cosine of 3 pi over 2 is 0, and the sine of 3 pi over 2 is -1. So this is -2, 4, 6, 8. This is -1. So it's coming around this direction. And at 2 pi, the cosine is back to 1, and the sine is back to 0. And so it's continuing towards that point. Okay. And so, yeah, it's not the best circle, but it does indeed appear to be a circle. Okay, let's go ahead and eliminate the parameter and see if we can verify that that's actually true. Now, this one, you know, in the previous one we solved for t and substituted it in. Solving and having inverse cosines or inverse sines is not the best thing to work with. And this one, what we might want to do is square both sides of this equation, so we get x squared equals cosine squared of t. And square both sides of this equation, so we have y squared equals sine squared of t. And then we'll just take and add those two together. So if we add on the left, we get x squared plus y squared equals, and if we add on the right, we get cosine squared t plus sine squared of t. Okay, and we know that sine squared plus cosine squared, no matter what t is always 1. Okay, so x squared plus y squared equals 1. So this is the Cartesian equation, and sure enough, this is a circle centered at the origin with radius 1. Okay, which is exactly what it looks like it was going to be. Okay, next we'll have another example. We want to see what curve is represented by this parametric equation. So it's similar to the last one, but this time, you know, we've got a sine for x instead of cosine, and it's 2t, and we've got cosine for y instead of sine, and it's 2t. Okay, but again, we're going to let t vary from 0 to 2 pi. So again, I've chosen just a few angle values for t to put in here, so just we can get a little bit of an idea of what it's doing. Okay, so we will start here. So when we substitute in 0, well, the sine of 0 is 0. Okay, and we substitute here, the cosine of 0 is 1. So 0, 1. Again, let's go ahead and do the 0.2, 0.4, 0.6, 0.8, and 1. Okay, so here's our initial point when t equals 0. Okay, if we move on to pi over 4 2 times pi over 4 is pi over 2. Okay, so we're talking about the sine of pi over 2, which is 1, and the cosine pi over 2, which is 0. Okay, so 1, 0 is here. Okay, so it's coming around this direction. Okay, this is when t equals pi over 4. When we get to pi over 2, well, 2 times pi over 2 is just pi. The sine of pi is 0. The cosine of pi is negative 1. So 0, negative 1 is down here. So it's coming this way. This is when t is pi over 2. And then at 3 pi over 4, well, we'll multiply that by 2. We're going to get 3 pi over 2. The sine of 3 pi over 2 is negative 1, and the cosine of 3 pi over 2 is 0. So now we're at 2, 4, 6, 8. Negative 1 is here. Negative 1, 0 is there. And then at pi, well, the sine of 2 pi is 0, and the cosine of 2 pi is 1. And so we're back up here where we started. So this is at t equals 3 pi over 4. And then here, we get back here at t equals pi. Okay, and then at 5 pi over 4, we're going to get 1, 0 again. So it's going to come down here. And then at 3 pi over 2, okay, we're going to repeat this. And we're going to get this 0, negative 1 again. At 7 pi over 4, it's going to come back around here. Okay, 2, negative 1, 0. And at 2 pi, it's going to be back up here again at 0, 1. Okay. And so if we look at the curve, basically it looks exactly the same as the previous one in the sense that it's a circle. So this also appears to be a circle. Okay, but you can see that they're not exactly the same because on this one, okay, we started here initial at the, I'll call this like the top. Okay, and then we went around twice. Okay, and we went clockwise. So in the clockwise direction. Okay, and so that's what happened with this set of parametric equations. Now this one, it also was a circle, okay, but the initial position was different, right? This one here, we start at, I'm just going to call this like the right. Okay, and notice we went counterclockwise and we only went around once. Okay, so we go around once and it was counterclockwise. Okay, so in a sense, these equations, you know, if I didn't have the arrows on there and they're both a unit circle. They both are a circle centered at the origin, radius 1, but they're not the same because if I look at the interval from t going to 0 to 2 pi and 0 to 2 pi, here we're talking about, you know, going once around in a counterclockwise direction, and here we're talking about going twice around in 2 pi in a clockwise direction. So if this were describing the movement of the particle, even though the path that the particle kind of lies on is the same, the number of times that it does it and the direction that it's going are different. And so there are differences between these parametric equations. And let's just show that you get like the same Cartesian description, even though the parametric curve is going to be very different. So if I squared, and I got x squared equals sine squared of 2t, and I squared both sides of this one, I got y squared equals cosine squared of 2t. And again, if I add those together, I'm going to get x squared plus y squared equals sine squared 2t plus cosine squared 2t. You know, it doesn't matter what this is. Sine squared of something plus cosine squared of that same thing is always going to be equal 1. So I get the same Cartesian equation, but the behavior of the parametric equation is different. Okay. And so that brings us to the idea of that there's a difference between a curve and a parametric curve. So we've shown in the examples 2 and 3 that I had two different sets of parametric equations and they represented the same curve. They both represented the unit circle. Okay, but we're going to distinguish between a curve like the unit circle, which is just a set of points, and a parametric curve, and in which we're taking those points and we're retracing them in a particular way. So here we might have a curve where it's just a set of these points, okay, but we don't have any idea of an initial point or a terminal point. We just, you know, that's a set of points. With a parametric curve, we see on here, oh well, at time 0 we start here, that's an initial point. And then as t, you can see t is 0, t is pi over 4, t is pi over 2. As we increase, we're going along the curve this way. But then we come back to this one at 3 pi over 4 and back to this one at pi. And so it'll come back and so this is both the initial and terminal point, but it moves along this path and back between 0 and pi. So this would be a parametric curve. We took all away the little arrows and the times, they would look the same. Okay, but when you put the times in there and the arrows in there, you can see that it represents something different. Okay. That's, I guess, we'll take a break here and go on to the next example. This is a good time to break.